Welcome to lecture number 13. This is Stereoisomerism continuation of lecture 12, where we started looking at stereoisomers, talking about enantiomers and diastereomers. So I'm just going to quickly review everything that we talked about in lecture number 12, the important parts at least. So I just drew some chiral molecule here in black. This chiral molecule has two chiral centers or two stereocenters denoted with those little stars. Okay, those are carbons that are connected to four different unique groups. So those stereocenters have either a wedge or a hash associated with them so that we know which stereoisomer we're talking about. Now, if we want to draw the enantiomer of this molecule, remember, all we do is we change all of the hashes to wedges and all of the wedges to hashes. So we invert every stereocenter while keeping the carbon skeleton the same. Remember, it's very important to make sure the carbon skeleton remains the same when you interconvert or draw the enantiomer. Okay, so the wedge becomes a hash, the hash becomes a wedge, and in blue here is the enantiomer. Now we have two diastereomers as well, remember, because 2 raised to the n, where n equals the total number of stereocenters. That's the total number of stereoisomers we could have. So 2 raised to the n would be 2 raised to the 2, which is 4 total stereoisomers. If we have 2 stereocenters, we'll have 4 stereoisomers. So we have 2 diastereomers, and we can get those simply by changing one stereocenter or the other, but not both. If we change both, that's the enantiomer. Okay, so these would be the diastereomers, the enantiomer, and the original molecule for a total of 4 stereoisomers. Okay. So moving on to the next part of this lecture, I just want to quickly mention mesocompounds. Mesocompounds are molecules with chiral centers. So I'm going to draw a molecule here that has multiple chiral centers. And a mesocompound is when you also have a plane of symmetry, which I just drew with this dotted line. So we can see we have a plane of symmetry, but we also have multiple chiral centers. So this would be considered a mesocompound, and these mesocompounds are achiral. These are achiral compounds. If we have a plane of symmetry with multiple chiral centers, it might look like a chiral molecule, but in fact, it is achiral. And why is it achiral? Well, let's draw the enantiomer of this. If we were to draw the enantiomer over here, we would simply change out the wedges, change out the hashes for wedges, get the enantiomer. But these are actually the same molecule. Okay, I drew what would be the enantiomer over here on the right, but it's actually the exact same thing. Why is it exactly the same thing? Well, if you took this molecule here and you flipped it like a pancake, if you simply flip the molecule over, you end up with the molecule over there on the right. So mesocompounds can take many shapes. I can draw another example of one down here. Say we have a carbon chain like this, and we have a wedged alcohol and a wedged alcohol. It looks like we have a molecule with 2 stereocenters, but we have that plane of symmetry. We have that plane of symmetry down the middle, so this is actually an achiral molecule. Okay. So how do we go about naming different isomers? Well, we use the Kahn-Ingold Prelog naming system, and we are going to call different stereoisomers either R or S. Okay, we can call either R or S for different stereoisomers, different chiral centers. Okay, so how do we do this? Well, let's draw a little example here, and we can work through it while we look at those rules. if we have a molecule like this, let's put a hydrogen and a chlorine. We have one chiral center on this molecule. Is this chiral center of R configuration or S configuration? Well, let's figure that out. Let's first go through the rules here. Rule number 1 is to prioritize all the groups on the chiral center, 1 through 4. And we prioritize based on the atomic number on the periodic table. So our highest priority group is going to be 1. Our highest priority group will be 1. And that's going to be the atom or the branch that has the highest atomic number. And then 4 is going to be our lowest priority group, and that'll be the lowest atomic number. So obviously hydrogen is going to be 4, atomic number of 1. What's going to be 3? 3 would be carbon. That's the next lowest atomic number here, followed by oxygen. And our highest priority is chlorine. That has the highest atomic number, comparing it to hydrogen, carbon, or oxygen. Okay, we're looking at that first atom branching out from the chiral carbon. Okay, so we have those numbered 1 through 4, highest priority to lowest priority. The next thing you do is you rotate the molecule so that 4, or your lowest priority group, is in the back. Now, as drawn here, hydrogen, our lowest priority group, is in the front. So how do we get it to the back? Well, I'm going to spin this molecule 180 degrees to simply rotate it so that it's facing in the back. So what I'm going to do is envision, let me take a blue here. I'm going to envision grabbing over here on those 2 blue carbons. And I'm simply going to twist the molecule in this direction. I'm going to twist it around like a carousel, twist it so that the hydrogen is not facing in front, but the hydrogen is now facing in back. This would put the oxygen over here on the left, the ethyl group chain over here on the right. It would put the hydrogen in back, and the chlorine would now be in front. Okay, hopefully you can see that. We're just grabbing either end of the molecule and twisting it, putting the hydrogen from the front to the back. So now the chlorine is coming out towards us. The chlorine is coming out towards us. The hydrogen is going back away from us. Now let's renumber these down here. 4, 1, 2, and carbon is 3. So 4 is now in the back. The final step here is to simply analyze groups 1 through 3 and determine if they're in clockwise order, which would be R, or counterclockwise order, which would be S. So groups 1, 2, and 3 are in this configuration, 1, 2, 3, going around that chiral carbon. So this is counterclockwise, which would be of S configuration. So this is an S stereocenter. If the chlorine was a wedge instead of a hash, that would be an R stereocenter. Okay, so every single stereocenter on carbons can be denoted with either R or S configuration, depending on how they are connected to that carbon. Okay, let's do another practice example. Okay, let's take a 5-membered ring. Let's draw a stereocenter here where we have an OH, and let's put a double bond right here. Now, is this chiral center of R or S configuration? Well, let's draw the hydrogen in just so we can see everything that's connected to that chiral carbon. Our highest priority group is going to be oxygen, because otherwise we have a carbon over here. Let's put it in red. We have this red carbon here. We have this blue carbon here. And then we have our hydrogen. Hydrogen is obviously going to be 4, our lowest priority. But we have a tie otherwise. We have a carbon and a carbon. So what do you do if there's a tie? Well, you simply look at what those carbons are connected to. In the case of the red, this carbon is connected to, it's double bonded to a carbon, and it has a hydrogen. So it's essentially connected to carbon twice, and then a hydrogen. What about the blue carbon? The blue carbon is connected to another carbon, and then connected to two hydrogens. So we're going to prioritize the red group, the red branch, over the blue branch because we have this additional carbon here, okay? A carbon is going to beat out this hydrogen since they're both tied. They're both a carbon in the first place. They're both connected to another carbon, but the red carbon is double bonded. So we're going to say it's connected to two carbons essentially, and this is going to be our higher priority group. So our red branch up here is going to be priority 2. And then this blue branch down here, priority 3. Now, we got lucky on this molecule because the hydrogen, our lowest priority group, is already in the back. So if we want to call this either R or S, all we have to do is look at 1, 2, 3. 1, 2, 3 are going in this direction, counterclockwise, which would be S. Okay, S configuration. So what does that mean the R configuration would look like? So if that's the S configuration, we can draw the R stereoisomer, which would simply be this. There's the R, here's the S. Okay. All right, so there's the S, there's the R. In this case, the S is a wedge, the R is a hash, but the hashes and wedges don't translate to S or R. It depends on what everything else is connected to. Okay, so you can't simply remember, oh, S is a wedge and R is a hash. That's incorrect, okay? Wedges can be S, wedges can be R. Remember, the wedges and the hashes are just relative perspective. S or R is determining the absolute connectivity of that stereocenter, okay? So moving on to the next topic here, I drew out R2-bromobutane and S2-bromobutane. If you're going to include the R or S configuration in the IUPAC name, you simply put it right before the word in parentheses, R2-bromobutane or S2-bromobutane. Now, there is one other way that we can identify different enantiomers, and that's using minus and plus. Now, this is an entirely different system, and R does not translate to minus, and S does not translate to plus. It's just that in this particular case, R is minus, S is plus. But this is an entirely different system. And what exactly is this system? This is the rotation of plane polarized light. The rotation of plane polarized light. This is what is causing either a minus or a plus. If this enantiomer on the left is dissolved in a certain solvent, placed in a polarimeter, and you introduce plane polarized light, R2-bromobutane happens to rotate plane polarized light in the negative direction, and S2-bromobutane happens to rotate plane polarized light in the positive direction. So you may also see negative and plus denoting different enantiomers, but more commonly you will see R and S. Now from this point in the lecture moving forward, we're going to get into more niche topics here. I'm going to cover them nonetheless, but if you are struggling with this chapter, everything up to this point, so all of lecture 12 and the beginning of lecture 13 is very important information. Okay, so spend most of your energy on that. But from now on, for the rest of the lecture here, we're just going to cover a few extraneous pieces of information. So considering minus 2-bromobutane, going to draw this here, an alpha in brackets with a 20 and a D. This is equal to negative 23.1. Okay, so what does this mean? Well, this is the specific rotation. That's the specific rotation. 20 up top is the temperature. And this D here is simply the wavelength. D is the wavelength. Now, under these conditions, minus 2-bromobutane rotates plane polarized light, a pure solution of minus 2-bromobutane rotates plane polarized light negative 23.1 degrees, negative 23.1. So what does that mean for plus 2-bromobutane? If we put plus 2-bromobutane, hopefully you can guess that plus 2-bromobutane, a pure solution of that enantiomer, would rotate plane polarized light plus 23.1. Okay, so enantiomers rotate plane polarized light in opposite directions, and it's one of the only differences between enantiomers is their rotation of plane polarized light. Okay, so this is an important phenomena. Okay, so thinking about this, what would happen if you had a 50-50 mixture? What would the optical rotation of a 50-50 mixture of both enantiomers be for bromobutane? If the minus enantiomer rotates minus 23.1, the plus rotates plus 23.1. If we had a 50-50 mixture of both, there would be 0 optical rotation. They would cancel each other out. This is called a racemic mixture. A racemic mixture is an equal mixture of both enantiomers, and it has an optical rotation of 0. So racemic mixtures are actually very common in chemistry because stereoselective reactions, or reactions that select specifically for one stereoisomer over another, are very hard to do. So if you're running reactions where you get a stereocenter, very often you'll end up with a racemic mixture, okay, a mixture of both enantiomers. The optical rotation of a racemic mixture is 0. So using this information, we can actually determine how much extra of one enantiomer we have over another. We can use plane polarized light and the phenomena that different enantiomers rotate plane polarized light in different directions to determine our enantiomeric excess, or the excess we have of one enantiomer over another. Okay, so let me draw that here. The enantiomeric excess, or EE, is the excess of one enantiomer over another. The enantiomeric excess. Pretty straightforward definition, so let's see how we can use it. Enantiomeric excess. If we know that minus 2-bromobutane rotates plane polarized light minus 23.1, plus 2-bromobutane rotates plane polarized light plus 23.1, and an equal mixture should have 0 rotation, Then if we have an unknown solution of two enantiomers, we can use plane polarized light to determine what concentration we have of each enantiomer. So again, this would be pure R for 2-bromobutane. This would be pure S for 2-bromobutane. And if we had an optical rotation of 0, then this would be a racemic mixture. Okay, so how can we use these to determine what we might have? Well, let's pose it as a question here. What is the EE of a sample of 2-bromobutane with a specific rotation of plus 14.1? What is the EE of a sample of 2-bromobutane with a specific rotation of plus 14.1? Okay, so it's not all the way up to plus 23.1, it's only 14.1. But since it's above 0, we know we have an excess of the S enantiomer, or the plus enantiomer, because it's on the plus side of 0. So let's set up this equation that can help us solve this. So the percent EE is going to be equal to the observed alpha, the absolute value, over the alpha of the pure enantiomer. Those are in absolute value brackets, and then we multiply it by 100, and that should give us our percent EE. Okay, so let's set this up. If we observe an optical rotation of 14.1, the pure enantiomer is 23.1. We divide those, multiply by 100, and that gives us an EE of 61%. 61% EE. So what does that exactly mean? It means we have 61% extra of one enantiomer over another. This means that we have 80.5% of the S, or the plus enantiomer, and we have 19.5% of the R, or the minus enantiomer, because the difference between 80.5 and 19.5 is 61. And we need these to add up to, obviously, 100%. So when we get this answer, 61% EE, we simply say it means that we have 61% more of the S enantiomer than the R enantiomer. So in a more simple way, if none of this made sense, and it all kind of went over your head, that's okay. This isn't extremely important information, but just as a simpler example to maybe visualize this, if we had a mixture that was 70% R and 30% S, we would have an enantiomeric excess of 40%. Okay, hopefully that makes more sense. If you have a mixture that's 70% R, 30% S, it means you have an enantiomeric excess of 40%, or you have 40% more of one enantiomer over another. Okay, so an EE of 0 would be a 50-50 mixture. Okay, an EE of 40% means you have 70% of one and 30% of the other. Okay, and we can analyze this mixture by using optical rotation. since enantiomers rotate plane polarized light in opposite directions. Finally, for stereoisomerism, I just want to touch briefly on the resolution or the separation of enantiomers. It's difficult to separate or resolve enantiomers because they have almost identical properties, physical properties. So enantiomers are essentially the same thing. They're very hard to separate because they have such similar properties. The only true difference they have, the real difference, is that rotation of plane polarized light. Diastereomers, on the other hand, have different physical properties, and it makes them much easier to separate from a reaction mixture. So how do we resolve enantiomers? Well, there's three different ways. Crystallization is one way. This was one of the first ways that enantiomers were resolved. Louis Pasteur separated out the enantiomers of tartaric acid and actually realized, he separated them by hand and realized that the different enantiomers crystallized differently. So he was able to separate them and actually resolve the enantiomers that way by hand. The next method for resolving enantiomers would be chiral resolving agents. And this is when you take a pair of enantiomers and you actually run a reaction in order to make a pair of diastereomers. You run a reaction, diastereomers, to turn a pair of enantiomers into a pair of diastereomers. And then once you resolve them, then you can turn them back into their original species. So a resolving agent essentially turns enantiomers into diastereomers. And the final method is chiral chromatography. This is a very specific type of chromatography or separation where you can actually place enantiomers into a chiral column, and the two enantiomers will separate out based on their very minute differences. So these are three different ways to resolve enantiomers. If anyone goes into process chemistry or research, you will be much more exposed to these. So I just want to introduce them as concepts. And if you do want to learn more about any of these methods, there's a lot of good information online. So again, lecture 13, stereoisomerism, a lot of new information in this chapter. We're going to do a workshop on stereoisomerism to really grasp these topics since they are very important. And then we'll continue on from there. Next video will be workshop number 6 for stereoisomerism, and I will see you there.